reaction of benzene with chloro or bromoalkanes and the Lewis acid catalyst produces alkyl benzenes. And the Lewis acid catalyst can, for example, be iron trichloride or aluminum trichloride. And this type of reaction is called Friedel-Crafts alkylations. And for Friedel-Crafts alkylations, we differentiate if the reaction takes place with a primary halogenoalkane or a secondary or tertiary halogenoalkane. And here we now start with the primary halogenoalkane and more specifically with the primary chloroalkane. So in the first step, the primary chloroalkane, which can also be described in this reaction as Lewis base, reacts with the Lewis acid catalyst, here the aluminum trichloride, to form a coordination complex. And hereby, the primary chloroalkane is converted into a stronger electrophile because, as you can see here, as indicated by this blue arrow, the electrons of the carbon-chlorine bond are now strongly attracted towards the positively charged chlorine. Therefore, this coordination complex constitutes a strong electrophile. Then, in the second step, benzene acts as nucleophile and attacks the partially positively charged carbon atom in this coordination complex. And you can see 2 electrons of the benzene molecule will here move towards the partially positively charged carbon atom, and at the same time 2 electrons will move towards this positively charged chlorine. And then we end up with a non-aromatic carbocation. Again, as we already know, this carbocation is only one of the 3 possible resonance forms. Then, in the third step, this non-aromatic carbocation gets deprotonated, and hereby we generate an alkyl benzene molecule where the aromaticity is regenerated, and we also produce hydrochloric acid and regenerate the Lewis acid catalyst, our aluminum trichloride. And what is now very important to see, if you have a look on our product, you can see that this is the first time in electrophilic substitution reactions of benzene that we produce a new carbon-carbon bond. So for all other electrophilic substitution reactions, we never saw the addition of a new carbon-carbon bond. And if we now use a secondary or tertiary chloroalkane, the reaction mechanism is slightly different, but we still produce alkyl benzenes. So let's have a closer look on the reaction mechanism with a tertiary chloroalkane here. So again, in the first step, this tertiary chloroalkane will react with the Lewis acid catalyst, and hereby we will form the coordination complex. However, it is now important to see that this coordination complex where the tertiary chloroalkane molecule is involved is now no longer stable. It will break down to form a tertiary carbocation and tetrachloroaluminate. And hereby, the rate of the formation of the carbocation from the coordination complex is dependent on the stability of the formed carbocation. And we remember that tertiary carbocations are more stable than secondary ones, and primary carbocations are the least stable ones. Hence, tertiary carbocations are formed quite rapidly from the coordination complex where tertiary halogenoalkane is involved. And this we can see here. And the secondary or tertiary carbocations are strong electrophiles. Hence, in the next step, 2 electrons of the benzene will attack the positively charged carbon of the carbocation. And then a non-aromatic carbocation is formed. And again, you know it already, this carbocation is only one of the 3 possible resonance forms. Subsequently, the last step takes place, which is the deprotonation of this non-aromatic carbocation. And we generate the alkyl benzene molecule as well as hydrochloric acid, and we regenerate the Lewis acid catalyst. After we now learned the reaction mechanism for Friedel-Crafts alkylations, it is important that we also have a closer look on the possible reaction products. And Friedel-Crafts alkylations generally yield multiple products, and particularly when using primary halogenoalkanes. And in the example here, you can see the reaction with benzene and 1-bromobutane, and the Lewis acid catalyst is iron tribromine. And as you can see here, we have a multitude of reaction products. So we have, first of all, this 1-butyl benzene, which is the expected reaction product. Then we also see 1,sec-butyl benzene and 1,4-dibutyl benzene. Furthermore, other substituted benzenes are also formed. And there are two reasons for these multiple products in Friedel-Crafts alkylations. First, rearrangements can take place, and second, polyalkylations take place. Let's start with the possible rearrangements. In the example, the first step is the generation of a strong electrophile, which is a coordination complex of the Lewis acid and the primary halogenoalkane. And this is depicted here. So this is what we normally expect when we talk about Friedel-Crafts alkylations, as we just learned. So we start with the formation of the coordination complex, which is a strong electrophile, based on the reaction of the 1-bromobutane with the Lewis acid catalyst. And this is then the resulting coordination complex. Subsequently, as we just learned, is then the electrophilic substitution reaction with benzene, and we end up with 1-butyl benzene as expected reaction product. However, this coordination complex can also undergo a rearrangement, which is a 1,2 hydride shift. And hereby, a secondary carbocation is formed, and this secondary carbocation is now more stable compared to the initial coordination complex, which resembles a primary carbocation if you have a closer look here. So you can see that the positive charge is at bromine, and this is in the primary position. Conversely, if we have this 1,2 hydride shift, we end up with this more stable secondary carbocation. So we can say that the driving force for this 1,2 hydride shift is the stability of the secondary carbocation. And then subsequently, the electrophilic substitution reaction with benzene follows. So we can see that we end up with this 1,sec-butyl benzene. And this product is also called rearranged product. So what is now important about the Friedel-Crafts alkylations? There is a 1,2 hydride shift taking place, which leads to a secondary carbocation, which is more stable compared to the coordination complex. And then the reaction product will be the rearranged product. And the other reason why Friedel-Crafts alkylations yield multiple products is that polyalkylations take place. It is difficult to only introduce one alkyl substituent because the substitution of one hydrogen atom by an electron-donating alkyl group makes the ring more nucleophilic and hence more reactive. So accordingly, it is favored to start further electrophilic substitution reactions as soon as the benzene ring has one alkyl substituent. And this is indicated here by this blue arrow. So we start with normal Friedel-Crafts alkylation, and then we end up with this 1-butyl benzene as first reaction product. Now you can see, based on this electron donating effect, we push the electron density into the ring, and therefore the ring gets more nucleophilic, and this favors further electrophilic substitution reactions. So then we continue the same type of reaction, and we will end up with 1,4-dibutyl benzene, which is a stronger nucleophile than 1-butyl benzene. And then we have the same effect. So now we have two alkyl substituents which are more electron donating, and therefore the ring becomes even more nucleophile. And then we continue with further alkylations. And we will end up with polysubstituted benzenes. And these polysubstituted benzenes will most likely not end up with 6 substituents. The reason for this is that if you have 6 quite large substituents on the benzene ring, then at some point steric hindrance appears, and then it is no longer favored to continue with the substitution reactions. So we will most likely end up with not fully substituted benzene rings. So what can we conclude? Electron donating effects lead to polyalkylation reactions and therefore for polysubstituted benzene products.